Okay, welcome to another, what is this, Stat 510? Stat 510 video. So today, or in this video, whenever you're watching it, we're going to sort of do a broad overview of statistical inference, which is more or less what we're going to talk about the rest of the way. So this is kind of our introduction point to the real purpose of this course, which is to talk about inference. Up to now, we've been dealing with a little bit of probability review, highlighting some things we're going to need along the way, but now we're really going to start to answer the type of questions that we're actually interested in. Okay, so this is kind of the setup that we're just going to repeatedly deal with, but I'm going to write this down all the time, and that is we have x1, x2 through xn, and they're assumed to be a random sample from some distribution f. And one of the questions we'd like to answer is, how do we infer f? If you were talking to, say, a computer scientist or someone maybe more interested in machine learning, they might say, how do we learn f? We kind of need to talk more about what we even mean by this really simple statement. So we drew a picture way back when in like one of the first lectures that sort of talked about this notion that there's these two sort of worlds. One is the population, or I'm calling it the data generating process, and we can use probability to answer questions about what the data would look like if we knew the data generating process. And that's what we've been doing up to now, more or less. But that's not really the goal of statistics. The goal of statistics is exactly the opposite. That is, well, we have some data. What can we learn about the data generating process from that data? So now we're going to go this way. So that's what we want to do now. That's not to say we're not going to be using probability. It'll be very important to understand what would happen if we actually knew the data generating process for doing certain types of inference. But ultimately our goal is, well, we have our one data set, and with that one data set, what can we then say about the data generating process? It's almost never going to be the case that we'll fully know the data generating process as a result of one data set. So often when we infer things, we're going to want to do them and then attach some notion of, well, we're not certain about this. There's some uncertainty still in what we think, and that'll be sort of important. So perhaps redrawing this picture a little bit to make it more specific. So now in the left circle, I have just some cumulative distribution function as a way to sort of represent a distribution or a population. And so the top arrow, what I'm going to draw is x1, comma x2, comma yada yada, xn. So think of this as this notion that these are random variables, right? So, and we can say we're going to randomly sample from this known distribution, and then what we end up with is what I have these little xi's for a particular realization of the data. Okay, and then what we're going to do is when we go this way, what we're ultimately going to do is apply some function to that data. Now, I'm being a little bit sloppy here, somewhat intentionally. So I've written g of the random sample, but I've made them uppercase x's again, that is capital letters, because while ultimately when we do get our one data set with the little x's, and that is, numbers or actual data there, we are going to apply some function to that, and that will spit out a statistic or an estimator that we're going to use. But we're also going to be able to analyze these statistics as if they were random variables. I would note that this thing here is a statistic. Because what is a statistic after all? Well, it is a function of data. And importantly, sometimes it's a random variable. So if you analyze the statistic from the perspective that it's a random variable, we can talk about properties of it when we assume certain things about the distribution on the left. Or if we input the actual values, that is the little xi's, well, then we're doing a calculation and it spits out some number on the other end. And that is what we'll use to sort of infer things from that population. It's kind of one of these really subtle things, but it's important to keep that in mind. Okay, so again, the usual setup is going to be we have this x1 through xn, assumed to be a random sample from some distribution f. And the question is, how do we estimate f? How do we learn f? How do we infer f? And we'd like to use a statistical model. And there are sort of two brands of statistical models that we're going to consider. One is parametric, and the other is non-parametric. I'm guessing when you took a previous class on mathematical statistics and you started getting into inference, you started with parametric models. And we're going to talk about some very basics of parametric inference in this video. But after the broad overview, we're actually going to start with non-parametric inference. That's one of my favorite things that the particular text that we're using does. Is it starts with the, in my opinion, more intuitive notion of non-parametric statistical models. So first, let's sort of maybe say a little bit more about what those two types of statistical models are. So again, assuming we have a random sample from some distribution f, what's a parametric statistical model? So what I have here is this notion of the set of all densities that are characterized by some parameter theta. So again, f is some density. And then this theta here is the parameter that determines the density. And this big theta here, well, that is what we call the parameter space, which are all the possible values that theta can take and give us a density that we want to be a part of our model. So that's kind of a bunch of jargon and notation. It's probably better to think of a specific example. So here, what we're doing is we're saying, okay, we assume we have a random sample from some distribution f, but now we're going to assume that the density related to this f comes from the model where the density is determined by some parameter p, and this here is what it looks like, and we'll say that p can take values between 0 and 1. This should look very familiar. So a much more succinct way to say this is, let's say x1, x2, comma, xn. So what we're really saying here is, oh, I guess it's time to get rid of me. Maybe we'll just make me a little bit smaller for now. Okay, so what we're saying here is that this random sample is assumed to be from a Bernoulli distribution with parameter p. And then in this case, the problem here is reduced to not learning some f, but learning the parameter p. So that is, in a lot of ways, I just need to mute my video. Bye. So in a lot of ways, that's very simple, right? We've even seen ways to estimate this p already. They're kind of obvious, but the downside is that we had to make an assumption. We had to assume that, well, this f is related to only these particular densities. Another quick example. Here we have x1 through xn, and I'm just saying normal, mean, mu, variance, sigma squared. Or actually, wait, no, I don't want to do that. I want to say this. Like that. We're assuming this is a random sample from some distribution f, and this time we're going to use a model where we assume the density, which is given by this thing here, and is now characterized by two parameters. So again, here we're defining our parameter space. And so here, perhaps, maybe we're interested in mu, right? Sometimes we use a statistical model, but we're actually just interested in maybe one or two particular parameters. Well, if we're interested in mu, then we would define sigma to be what we call a nuisance parameter. And again, I spoiled it because I had a typo here. A much more succinct way to say this would be like this. So we would say that we're using a model that says, well, we believe these data were a random sample from a normal distribution with mean and mu. And now instead of just learning f, this unknown distribution, we just have to learn two parameters instead. Okay, so what's the alternative? Well, let's say we have some random sample that's assumed to come from some distribution f. Let's assume that f is from the set of all possible CDFs. And then we will use a non-parametric approach. We won't get into the nitty-gritty details of what it means to be non-parametric versus parametric, but here we assume something, and then the problem reduces to learning some parameters. Here, we're assuming essentially nothing. We're just assuming that, well, f is a CDF, and then we're going to attempt to learn it. That will be what the entire next video is about, but for now, that's just the big difference. Parametric models, we assume something about the model and then learn the parameters. Non-parametric, you assume the most simple thing possible, which is that f is a CDF. Okay, so a quick note here. We don't need to say that frequentism is better than Bayesianism or vice versa, but I will say that for most of what we're going to see going forward, we will be considering the frequentist interpretation of inference. That's not to say that it's better, but that will be the sort of the interpretation of probability that we'll be using when thinking about a lot of these things. We'll make some references to Bayesian inference along the way, but then what we'll do is later on down the road, we'll come back and specifically talk about Bayesian inference and then do a comparison between the two. But for now, we're almost always talking from a frequentist perspective. If you don't know what this means, it doesn't actually matter for now, but we'll be living in a frequentist world. Okay, so when it comes to inference, there's basically three broad things that we're going to want to do. One is we're going to want to make what we call point estimates. And that's basically saying, well, there's some unknown quantity that I want to learn. I'm going to make a best guess. Like, I'm going to give you one number that is my absolute best guess for that unknown quantity. But point estimation is often related to interval estimation that says, well, there's some unknown quantity. Rather than giving you my best guess, I'm going to give you a range of values that unknown could take, with hopefully, that interval was designed in a way that often the true value will be inside of the interval. And then the last thing will be hypothesis testing, wherein we assume some value of an unknown quantity, and then perhaps gather some data and then reevaluate our hypothesis. Okay, we're going to spend a little bit of time talking about point estimation, a little bit of time talking about interval estimation, and then a very brief mention of hypothesis testing in this video. But anything I say in this video is only for introductory purposes. We're going to hit all of these topics in detail throughout the coming weeks. Okay, point estimation. So like I said, we basically want to come up with some way to make a best guess for some theta. So we're using theta hat as a point estimate for theta. And so theta here is what we call our parameter of interest. And related to us, for now, taking the frequentist approach, theta is fixed but unknown. So it's not random, it's just that we don't know the value. Okay. So I should maybe put a subset in here just to be consistent. So, although I will often not, so just a note there. But anyway, so now back to the setup that we normally have. We have some x1 through xn, which is a random sample from some distribution f. We define theta hat to be some function of the xi's. That's interesting. So we have a function of the data. Hey, that sounds kind of familiar. That's basically a statistic. But when we're talking about using it for the purpose of estimating some unknown quantity theta, instead, we will often call this a point estimator. Okay. But like a statistic, we can often evaluate this thing with as if it were a random variable. And one thing to note here is that, well, because this is a random variable, it has a distribution, and that distribution would be called the sampling distribution. Okay. So a few definitions related to estimation. First, we have the bias of an estimator, which is equal to its expected value minus the thing that you're trying to estimate. If this is 0, then we say that the estimator is unbiased. Historically, bias gets a lot of attention in the statistical literature. We traditionally have really liked unbiased estimators. It turns out that that's not always what we want. Sometimes adding a little bias can greatly reduce the overall error in your estimation, which is the mean squared error that we're looking at here. But so quickly then, the variance of an estimator is just, plugging into the definition of variance, so nothing interesting there. But so the mean squared error is maybe a better metric than bias or variance. It turns out to be related to both of them. But it's saying, in a squared error sense, how far away is our estimator from the true value on average? And it turns out that this is equal to the bias of the estimator squared plus the variance of the estimator. The proof of this relationship is in the book, but I would suggest you try to do that yourself real quick. It's not too difficult. It's just following the rules of expectation. There's one little trick, and perhaps you've seen it before, so we won't do that here. But that is something that I would recommend going through. So I'm sort of contractually obligated to now show pictures of a bullseye to illustrate the concepts of bias and variance. So here we have 4 examples. And so I think sometimes these targets are hard to understand because we're often thinking of a one-dimensional problem, but then we make it two-dimensional. So what's going on here? So the bullseye is basically the theta that we're trying to estimate. And then, so for example, this point here is theta hat for some data. Well, and then this point here is also a realization of theta hat for different data. And so on and so forth. So in the top top left up here, this is what we ultimately want out of an estimator. It's low bias, that is, sort of, if you think about like an averaging of these points is very close to the center, and low variance. The points are close to each other. If we move to the right, this looks to be unbiased. Like on average, the points are still probably around the center, but they're spread out amongst each other. If we go down here now, well, this is variable still, but there's bias, right? Instead of being on average here, it's on average like here. And then going over to this picture here, now the bottom left, clearly the center's here, but the average of these things is somewhere here. So it's biased, but the points are, closer together than these. So it's low variance. The question is sort of, well, would you prefer an estimator that produces results like this or an estimator that produces results like this? But remember, in practice, you only get one data set, right? So if I randomly pick one of these, well, there's the error that it makes, right? Where if I randomly pick one of these, maybe there's the error it makes. So that's exactly why we have something like mean squared error, though, because it tells you exactly one number that sort of takes into consideration both the bias and the variance. If you've ever taken a machine learning class, you've probably heard of something called the bias-variance trade-off, where depending on the complexity of your model, you can manipulate how much bias and how much variance there is. Okay. Anyway, so one important definition to sort of tie that all together is this notion of if we have some point estimator theta hat sub n of the parameter of interest theta, we say that it's consistent if theta hat converges in probability to theta. So these are, if an estimator is consistent, it's an estimator that gets better with more data. And hey, that's good, right? We wouldn't want our methods to get worse with more data or stay equally bad with more data. Like the more data, the closer it is we're going to be to the thing we're trying to estimate. That's good. We like that. Okay, so quickly, you might already see how this works, but if we have an estimator with bias that is going to 0 as n goes to infinity, and variance going to 0 as n goes to infinity, well then that theta hat is indeed consistent. The proof here is perhaps easy. So I think you should see that if bias and variance go to 0, then mean squared error goes to 0 as n goes to infinity. Well, if mean squared error goes to 0, then we have theta hat sub n converging in quadratic mean to 0. Or sorry, not 0, theta. Which is kind of clear from the definition of mean squared error. It's exactly the thing we want to go to 0 in the definition of converging the quadratic mean. And then so we finally get theta hat sub n converging in probability to theta. Cool. So, and this is maybe a first idea towards, well, we don't need an unbiased estimator. We just need an estimator that has bias that shrinks with n. So we probably wouldn't want an estimator that doesn't have bias shrinking with n, but we are okay with a bias estimator. Okay, so I need to return for a second here. So a note about this thing people call standard errors. So I'm a big fan of the book we're using. Really like this book. By the way, if you're an Illinois student watching this, and if you're not, that may be surprising, but through the library, we have access to the free PDF copy of the book, which is wonderful. but also through a similar service, if you want a paperback version of it, you can get it for only $25. I guess this is free advertising for the book, but I figure we're using it. If you want a copy, I love having just a paper copy that I can reference whatever. Anyway, one of the only things that I don't like about this book, and I love like everything about this book, one of the only things I don't like is one sort of notational issue. So, and this is not necessarily a qualm with just specifically this book. This is a beef I have with the entire field of statistics. So often we'll talk about these things called standard errors. And the way this book defines it, which is one way to do it, is to say that the standard error is basically the standard deviation of the estimator. And that's fine. But then we have to also say, well, sometimes we have to estimate that quantity. So we also have an estimated standard error. So that's the two things I have here. So for me personally, I think this is a lot of jargon that we don't need, because another word for the standard error is just the standard deviation of the estimator. Another name for the estimated standard error is just an estimate of the standard deviation of the estimator. I genuinely don't understand why we have to introduce new notation just because we have an estimator, but many people do it. My problem is that, and again, this part is definitely not a knock against the book because the book is consistent about this, but the field of statistics mixes up these things sometimes. And not, I guess, mix them up, but sometimes people only refer to this quantity as the standard error. Some people refer to it as the estimated standard error, and that's confusing. So I just don't understand why we can't call things the standard deviation of the estimator and the estimated standard deviation of the estimator, because that's literally what the terms are. I think that's easier, but I don't know. I've never heard a convincing reason why not to use the notation in blue, but know that in the book, they'll use little se for the standard deviation of an estimator and little se hat for an estimation of that standard deviation, because it's often unknown. Okay, that was a quick rant, but I don't know. I think it's important. Okay, bye. On to an example. So let's say that we have a random sample and we assume it to be from a Bernoulli distribution with parameter p. Okay. So first, we'll define an estimator for p to be the sum of the xi's over n, the sample mean, if you will, or the sample proportion, because we know that the xi's here can only take, 0 and 1. So we can quickly find the expected value of p hat. We've pretty much done that before. We find that it's p. Therefore, p hat is unbiased. We can also calculate the variance of p hat. It's just the variance of xi divided by n. We've seen that kind of thing a bunch of times. And so in my notation, we would say the estimated standard deviation of p hat is what we see here. But again, this would be se hat in the book notation, which is the estimated standard error. Okay. So since p hat is unbiased, and the variance of p hat, oh gosh, that's a bad bracket. The variance goes to 0 as n goes to infinity. Well, then we conclude p hat is consistent. Great. So that's a perfectly reasonable estimator for p from a Bernoulli distribution. Okay, so one thing that's going to come up in estimation a lot is this idea of the asymptotic normal. So if we have some estimator, and if we subtract off its mean and divide by the standard deviation of the estimator, otherwise known as the standard error, and it converges in distribution to a standard normal, we would call this asymptotically normal. And that'll be useful for things like making confidence intervals, which we'll talk about now. Okay, so we often talk about this notion of a 1 minus alpha confidence interval for theta. And right away, I'm going to remind you that theta is not random. So a confidence interval is an interval. We'll call it C sub n, and it has endpoints A and B, both of which are functions of the data. And because of that, A, the lower bound, is random, and B, the upper bound, is also random. So if this A and B are constructed in a way where the probability that theta is between A and B is greater than or equal to 1 over alpha, which we call the coverage, for all theta, then this thing is a 1 minus alpha CI. So I'm probably going to belabor this point a lot in this video, but remember, we can calculate a probability here because A and B are random, but remember, theta is fixed. It is not random, so that is not the thing that allows us to calculate a probability here. Okay, so thinking about the interpretation real quick before we even get to looking at an example. So the first thing I have written here is how to calculate a 95% confidence interval for P in that Bernoulli example we were talking about. So this is random. So depending on the data you get a different interval here, and the data being randomly sampled, we have randomness. So here we can make probability statements. But now, let's say we actually get some data and calculate an interval like I've done here. There is nothing random here. So, as a result of there being nothing random, that is 0.48 minus 0.07. That's not random, except perhaps if you ask a 2-year-old who doesn't understand how to do subtraction, but we'll say we can. So that's not random. 0.84 plus 0.07, also not random. And theta, or P, what we're trying to capture here, is not random. So there's nothing random. So as a result, you cannot make probability statements. So the idea is that it's the method that works with some probability, 1 minus alpha. It's not an individual interval. So if we say that like I use this method to make an interval today, and then I make a different interval on different data with the same method tomorrow, and so on and so forth, I can say ahead of time that like 95% of those will contain the true value, but about any individual interval, I cannot make a probability statement. Is that an annoying pedantic thing? Yes, but that is technically correct. For an example of sort of maybe some absurdity here, I want to talk about an example. I didn't get the exact citation. I forget the year on this, but an example that comes from Berger and Wolpert that sort of shows the oddities of thinking about probability statements with respect to confidence intervals. So we're going to define two random variables, x1 and x2, that are independent, and they take values 1 and -1 equally often, that is probability 0.5. So then we define yi to be some theta, and theta is what we're going to be interested in here, plus xi. And then we'll only observe y1 and y2. We won't observe the xi's. So now we're going to define an interval. And it's not really an interval. It returns a single value. But so if y1 and y2 are both equal to each other, we're going to return the quantity y minus 1. And that will be our quote-unquote interval, the single value y minus 1. If y1 does not equal y2, then we'll return the average of those two. And so what we can say then is the probability that theta is contained in that interval is 3/4. And again, it's the c that's random. It's not the theta that's random. And this is for any theta, which implies that this is a 75% CI. Okay. So, if it might be hard to see without doing a little work why that is 75, but note that if we consider the possibilities of x1 and x2, they look like this. -1, 1, -1, 1, right? So if x1 and x2 were both 1, then we would correctly have theta in our interval because we would subtract 1 from y1 and we would get the right answer. If they're both different, well, then we're in here and we'll be correct. But if they're both -1, then we'd come back up here, except this time we would be wrong. So this is not an interval. Right. Okay, so 75% of the time we'll get it right. But now let's say we observe y1 is 15 and y2 is 16. Well, this implies that theta is 16 given how the y's were defined. We just know that. Well, in that case, the probability that theta is contained in C given y1, in this case, is not equal to y2, well, that's 1, right? So there's kind of a... So we would never be able to calculate this for most practical problems, but that kind of shows you a little bit of the oddity of what's going on. So this is the definition of the confidence interval, but this is a statement that you might be more interested in sometimes. I would note that we're starting to flirt with some Bayesian ideas here, but we won't get there quite yet. But when we get to Bayesianism, we'll allow ourselves to make statements like, hey, the probability that this interval contains a true value is some probability. And you can do that, but those won't have the frequentist coverage probabilities necessarily. And that's a whole conversation for later. But if you know anything about these two, the fact that I bring up Bayesianism is sort of not surprising. Berger, I think, wrote one of the foundational texts in decision theory and Bayesian analysis. So sort of no surprise. Okay, so I mentioned that, if we have this limiting distribution that's normal of our estimator, so in this case, if we have some estimator that we could approximate with a normal, with the mean, that is the parameter we're looking for, and some variance, which is the estimated standard error squared, and we define this z sub alpha over 2 value, then this Cn gives us a 1 minus alpha confidence interval. So for example, if we have alpha equals 0.05, that implies that z sub alpha over 2 is 1.96, which a lot of people will say is just 2. Only statisticians will believe that 1.96 is equal to 2. But anyway, so then an approximate interval is given by theta hat plus or minus 2 times the estimated standard error. This probably isn't shocking. This is probably something you've seen many times. The justification for that is given here, where we simply are first doing the probability calculation about the interval we defined. This is just doing some rearranging, which I imagine. So we, subtract off theta n divided by standard error, multiply by -1, and do all that good stuff. So then we leverage the fact that this is approximately normal. So then this is something like this, which is by definition exactly 1 minus alpha. So there we go. So that's the justification for the usual quote-unquote normal interval. Okay, so wrapping up real quick, just a quick note about hypothesis testing. So hypothesis testing will assume, well, at least in parametric settings, which we'll talk about, we assume we have some random sample that's from some distribution that's parameterized by, in this case, p. Well, then we can specify what we call the null hypothesis, which says that p is 1/2. So you can imagine we're saying flipping a coin, what's the probability of heads? Well, I'm going to assume it's 1/2. H1 is what we call the alternative. Oh, I can't spell. Alternative. Which is basically all the other, in this case, all the other possible values that p could take. And what we want to do then is, so we come up with some statistic. So what I have here is p hat, which is the proportion of, say, heads we observed in a coin flipping example, minus 1/2, and the absolute value of that. So I think it's clear to say that if this quantity is small, well, then we have no reason not to believe the null hypothesis. But if this quantity is really large, so like if p hat is something like 9/10 or whatever, well, then this quantity is big, right? And that might sort of, shed some disbelief on the null hypothesis. So the general idea is that we reject, that is, we no longer believe the null hypothesis when this statistic t is large. So the question that we're going to sort of tackle is, well, how large? How large do we need to make the statistic before we reject for it to be a sort of well-formed hypothesis test? So that's what we'll be talking about down the road. Right. So that was sort of a brief, far too fast, possibly at times confusing introduction to all the things we're going to do in the rest of this class. So if any particular thing wasn't super clear here, don't worry about it. In the next video, we're going to sort of put our focus onto just one specific thing, and that one specific thing will be using non-parametric estimation to estimate that f, that CDF of the distribution that we believe the random sample came from. Okay, so that's it for now. As always, if you made it to the end of the video, good job. And I'll see you in the next one.